At the lowest mathematical level, generating artificial intelligence requires executing a massive, highly predictable series of matrix multiplications. Billions of parameters multiply against incoming data, layer by layer, to predict the next token. Because this specific mathematical workload is so predictable, hardware engineers typically default to building application-specific integrated circuits, or ASICs. When you know exactly what math you need to run, you build a chip designed to do exactly that math and nothing else. This chart shows the architectural divergence. On the left, an ASIC like a tensor processing unit utilizes a rigid systolic array. Data flows through it in a single predetermined direction, performing continuous matrix multiplies. On the right, a graphics processing unit devotes precious die area to complex routing, warp schedulers, thread switching, and varying memory banks. All of those extra components on the GPU side are the overhead required to support general-purpose computing. They exist so the chip can handle irregular memory access and heavy branching. Stripping out that overhead allows an ASIC to dedicate nearly all of its silicon directly to raw computation. On paper, this makes the ASIC the mathematically superior and most elegant solution for processing static AI workloads. The empirical market data contradicts this theoretical advantage. General-purpose accelerators, specifically NVIDIA's GPUs, maintain the vast majority of market share across the AI industry, sustaining gross margins above 70%. The largest hyperscalers in the world, companies like Amazon, Google, and Microsoft, have the capital and engineering talent to design and deploy custom silicon, yet their external cloud infrastructure and commercial AI factories rely overwhelmingly on GPUs. This creates a distinct paradox. The world's most sophisticated technology companies are paying a massive premium to purchase general-purpose overhead they theoretically do not need. The resolution to this paradox is that the primary constraint on frontier AI capability is not raw matrix multiplication throughput. The actual bottleneck is the rapid pace of algorithmic evolution. When the underlying computer science changes every single year, strict hardware programmability. Scaling hardware performance has historically relied on standard lithographic node shrinks. Semiconductor foundries physically reduce the size of transistors, migrating from a 5-nanometer process down to 3 nanometers, allowing more computational power to fit on a single piece of silicon. This chart plots Moore's law, representing a steady physical limitation. Relying solely on transistor density yields roughly a 25% performance improvement year over year. However, the compute capacity delivered to AI labs recently has completely detached from this steady linear curve. Moving from the Hopper architecture to the new Blackwell architecture yielded a performance and energy efficiency leap of roughly 30 to 50 times. This is the Blackwell platform. Its specification shows scaling capable of addressing trillion-parameter generative AI. Generating a 50x leap over a 3-year cycle is physically impossible to achieve purely by packing transistors closer together. The limits of silicon physics dictate that density alone cannot produce that delta. That massive performance jump is the result of deep architectural and algorithmic co-design. Engineers are simultaneously optimizing the processors, the NVLink interconnect fabric, the network, the libraries, and the algorithms themselves. Relying strictly on hardware physics is a losing strategy. Exponential performance gains occur only when the software stack can radically reshape how the hardware is utilized. AI research is currently migrating away from traditional monolithic dense models. This visualization shows the mixture of experts architecture, or MOE. It is a complete rewriting of how an AI model operates. Instead of one massive dense structure, MOE models are disaggregated. The workload is distributed dynamically across multiple experts, residing on different processing nodes across a massive computing system. Handling these dynamic shifts across a network, or introducing fuse-diffusion techniques and hybrid state space models, entirely breaks the rigid routing pathways baked into an ASIC. This is the specific function of CUDA. It provides researchers the ability to write custom computational kernels down to the C++ level, directly controlling how the hardware executes logic. Because they have kernel-level access, research labs can invent and test entirely new attention mechanisms over a weekend. They do not have to wait years for a foundry to print new specialized silicon to test a new mathematical theory. Hard-coding silicon to execute today's optimal algorithm guarantees suboptimal performance for tomorrow's algorithmic breakthrough. The financial premium companies pay for GPUs serves as an insurance policy against immediate algorithmic obsolescence. Looking at a single chip misses the economic reality of the modern AI facility. The true constraints exist at the scale of physical infrastructure. In a gigawatt-scale data center, the absolute hard ceiling on scaling is the available power supply, not the initial procurement cost of the silicon. This equation governs data center profitability. Tokens per watt equals algorithmic efficiency multiplied by hardware flops divided by energy consumed. The most critical variable here is algorithmic efficiency. When engineers update a programmable GPU with a new, highly efficient algorithm, they drastically increase the numerator. This skyrockets the tokens per watt output of the entire data center without requiring a single new watt of electricity. Procurement cost is only one fraction of the total cost of ownership calculated over the multi-year lifespan of the hardware. Because an ASIC cannot adopt the latest algorithmic efficiencies developed by the research community, its tokens per watt ratio degrades relative to the state-of-the-art over time. This makes it economically inferior over its life cycle, regardless of how cheap it was to buy on day one. The AI industry operates as an interconnected 5-layer stack: energy, chips, systems, models, and applications. By supporting every framework, NVIDIA transitioned from a chip vendor into a universal deployment fabric. Consider the economic dilemma of an independent researcher building a new open-source framework. Developers naturally write software optimized for the hardware that possesses the largest existing installed base. This guarantees their product achieves immediate global distribution. This creates a compounding dynamic. The hardware that is most abundant continuously receives the sharpest software optimization from the widest pool of global engineering talent. Writing software for specialized hardware forces developers to take on the massive risk of porting custom code for a comparatively tiny audience. The flexibility of the architecture creates an insurmountable software network effect, locking in the economic advantage of the general-purpose chip. There is a specific scenario where this dynamic reverses, known as architectural stagnation. This is the theoretical point where artificial intelligence model design stops evolving entirely. Specialized ASICs will definitively conquer the hardware market when AI mathematics becomes a perfectly static, commoditized utility, requiring no further algorithmic experimentation. The current pace of frontier AI research shows no evidence of stagnation. Labs are rapidly combining diffusion, reinforcement learning, and custom routing into entirely novel architectures. Surviving this era of computer science requires computing hardware that can physically mutate its logic alongside the science. Until the science of artificial intelligence reaches a definitive dead end, general-purpose programmability will maintain its absolute superiority over specialized silicon.